Okay, on to question 2. So this problem is asking you to do some arithmetic operations, some compare instructions, and then kind of try to understand what the status bits are doing and how that relates to branches. And so let's go through these. So the first instruction, add S, R3, R0, R1. So we're adding R0 plus R1 here. We'll take those values from the registers. So R0 is 0x85 plus 0x93. And then I'm going to write that out in binary so we can see what happens when we do this add. So that's 1000 for 8, 0101 for 5, plus 1001 for 9, 0011 for 3. So let's just work that through. So 1 plus 1 is 0, carry the 1, 0, carry the 1, 0, carry the 1, 1, 1, 0, 0, 0, carry the 1. So we have a carry out of 1. So that's our C bit. We know that that's going to happen. And if we look at this, we added a large number plus a large number. So we know that there's going to be unsigned overflow, right? We added a negative number plus a negative number, and we got a positive number. So we do have signed overflow as well. That's the error case there. And we can look at it, right? We added two negative numbers together. We got a positive. Doesn't make a lot of sense, right? And then 0, it's not 0, so this is z equals 0. And negative, it's not negative because our first bit, or the leftmost bit, is a 0, so that's going to be a 0 as well. So that's our result for the add S. For the CMP, CMP is R2 minus R1, set flags, right? That's all that happens. It's a side effect instruction, right? So it doesn't actually compute that result anywhere. I should add for this first one, R3 is going to change to our result here, which is 0x18. Sorry, I missed that. So that was the first instruction, the add there. For the CMP, we do this operation, but we don't actually store it. We just set the flags so that the branch instruction following it can use it. That's usually how this works, is we have a CMP and then some sort of branch instruction to do control flow. So for that instruction, we're going to do R2 minus R1, and that's going to be from our registers, 0x99 minus 0x93. In binary, that's going to be 99 is 1001, 1001. And we're going to do this addition via subtraction, right? So we need to know what 93 looks like in 2's complement. So we're going to invert 0, 1, 1, 0, 1, 1, 0, 0, plus 1. So 0, 1, 1, 0, 1, 1, 0, 1 is our value to add. That's the 2's complement. That's negative 9, 3 hex, right? So 0, 1, 1, 0, 1, 1, 0, 1 is what we're adding together. Got 0, carry the 1, 1, 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, and then we carry out C equals 1. So our result was 0x06, right? We had a carry out, so we're setting that flag, and we could see again, we basically added a large number plus a small number, and we got a small number, which is not what we expect in unsigned math, right? We should get large number plus something should still be a large number, but we overflowed, so we don't have that. We have a negative plus a positive is a positive, which is okay. That's what's expected to happen in unsigned math, so it's not signed overflow, so that's a 0. Our result is non-zero, so z is 0, and our result is positive, so n is also 0. The BNE instruction doesn't update our flags, right? It uses the flags. So we're trying to figure out what happens here. Do we execute the add instruction, or do we jump to lab, the lab label over here, right? So BNE is going to jump to the label if the condition is true, and that's NE is what we're looking at here. So if not equal is true, we're going to jump to here and we're going to execute that instruction. If not equal is false, we're going to fall through and execute the add instruction. So did our comparison return that they were equal? Well, NE looks at z equals 0. So if z equals 0, we make the jump. And really, we can think of this as like we did the comparison. If those two numbers were not equal, we're going to jump to the label. So this is going to cause us to jump over the add instruction and go to that label, the lab label. And then we're going to do the ASRS. So we skip this add instruction here. We don't have to do that. We shouldn't see an update to R4. we should see an update to R5, which is an arithmetic shift by 1 from R0. So we're taking 8.5 and we're shifting it over by 1. So we initially have 1, 0, 0, 0, 0, 1, 0, 1. We shift that over by 1 place, and that's going to give us 1, 0, 0, 0, 0, 1, 0. And we need to fill in that leftmost bit here to determine what we're going to do with that. Because it's an arithmetic shift, we are sign extending as we shift. So our final result here in hex should be C2. And that's just, we group the 4 digits, we group those 4 digits and convert them to hex. That's it for that problem.